Today's science anniversary. It is the birthday of this guy, Robert Cornelius, who was an early photographer. He took a photograph of himself in November of 1839. He was the first selfie guy. So happy birthday to the first guy who ever took a selfie. We're going to talk about mole ratios and balanced equations. Again, oodles and oodles of math. So have your calculators ready. Lots of gram to mole conversions. So have your periodic tables ready. Get set. There will be another quiz on Wednesday, so definitely think about spending some time with the homework. Go. So just a quick little bit of definition. We've been talking this whole unit about stoichiometry. Well, we haven't been talking about stoichiometry. We have been, but I haven't exactly defined it. So stoichiometry, which is the name of our unit, is just the math of chemical reactions. It's all about us scaling chemical reactions so that we would scale recipes. Had a cookie recipe, and that recipe made 24 cookies, but you actually needed to only make 12. When you needed to make 200, you would scale things up. Stoichiometry is all about us scaling these chemical recipes, really just what a chemical equation is. So chemical equations are basically recipes for us to make stuff in chemical reactions, and sometimes we have to scale them. We use our balanced equations to do that scaling. Balanced equations tell us a lot. So all the things that we can learn from a balanced equation. So let's say that I'm looking at this equation where I'm taking nitrogen gas and hydrogen gas, and I'm making NH3. Anyone remember what molecule, what is our common name for nitrogen trihydride? What do we call it in everyday language? We use it to clean stuff. We use it to make fertilizer. What is it? Anyone? Oh, it is ammonia. Perfect. My pen just turned itself off. It is ammonia. So this is our balanced chemical equation for making ammonia out of nitrogen gas and hydrogen gas. We need one molecule of N2. So here's that one N2. We need 3 molecules of H2. There's 1, 2, 3 molecules. Each of those little blue guys is a hydrogen atom. And then we can make 2 molecules of NH3. 1 N and 1, 2, 3 H's. 1 N, 1, 2, 3 H's. So that balanced equation tells us that I'm going to take 2 atoms of nitrogen and 6 atoms of hydrogen. 2 times 3 makes 6. Then I can have 2 atoms of nitrogen and 6 atoms of hydrogen, just like I started with. Conservation of matter, right? 2 nitrogens, 6 hydrogens. I can think about this in terms of molecules. I could have 1 molecule and 1, 2, 3 molecules, and I could make 1, 2 molecules of ammonia. I could scale that up a little bit and make 10 of these guys, 30 of these guys, form 20 of these guys, just by multiplying everything by 10, scale up by 10. 1 times 10, 3 times 10, 2 times 10. I could also scale everything up by 6.02 times 10 to the 23rd, which is a mole. So I could have 1 mole of nitrogen gas and 3 moles of hydrogen gas. And that would make 2 moles of ammonia. So I can think of my equation in terms of molecules or moles. I can use my moles to figure out mass by using the mass given to us on the periodic table. So if I have 1 mole of nitrogen gas, nitrogen on the periodic table is 14.007 times 2. By around 14.007 to just 14, that's going to give us 28. Do the same thing for hydrogen and ammonia, and we should have equal masses on both sides. Law of conservation of matter. Remember that we also have volume. I can take my moles and turn them into volumes. So 1 mole at STP would have a volume of 22.4 liters. 3 moles at STP would be 3 times 22.4, 67.2 liters. 2 moles here times 22.4 liters would give us 44.8 liters. If I add these up, do they equal the volumes of the products? Does the law of conservation of mass also translate to a law of conservation of volume? Definitely not. So I've got 22.4 and 67.2 adding up to make 44.8. The reason that the volume is so much less is because I'm packing more pieces together. So instead of having 1, 2, 3, 4 molecules of gas floating around, now I only have 2. So my balanced equation can tell me oodles and oodles about what's happening in my reaction. So let's say that I had this equation: hydrogen sulfide is found in volcanoes. It can react with oxygen gas in the atmosphere to form sulfur dioxide and water. I could say that if I have 2 molecules of this guy and 3 molecules of this guy, they smash together and rearrange, I can form two molecules of SO2 and two molecules of water. Or I could think about it in terms of moles. Same equation, 2 moles of H2S, 3 moles of oxygen, and I can form 2 moles of sulfur dioxide and 2 moles of water. So molecules or moles. Moles is what we're going to focus on the rest of today. I can use my balanced equation to put together some ratios of the mole numbers from the balanced equation. So let's say that I've got nitrogen to hydrogen. I want to know what's my ratio of nitrogen to hydrogen. Well, it's 1 to 3. 1 to 3. What if I wanted to make a ratio that was nitrogen to ammonia? What numbers would I add to my ratio to have a ratio of nitrogen to ammonia? What should I put on top? 1, of course. What should I put on the bottom? Oopsie. 2. So I can build a ratio of nitrogen to ammonia. 1 mole of nitrogen is required to make 2 moles of ammonia. I could also put together a ratio of hydrogen to ammonia. What would be my ratio here? 3 hydrogens to 2 ammonias. 3 to 2. I could also take the reciprocal of all of those. Math people, tell me, what even is a reciprocal? What's a reciprocal? What should I do to my ratios? How do I get a reciprocal? Do what? How do I find a reciprocal? I just flip it. Exactly. We flip it. So instead of 1 N2 to 3 H2, I could say that I have 3 H2s to 1 N2. That's another mole ratio. Same thing here. I could have a ratio of 2 ammonias to 1 nitrogen. I could have a ratio of 2 ammonias to 3 hydrogens. So I'm just taking those coefficients from my balanced equation and I am putting them into pairs to build mole ratios. Mole ratios. Why does that matter? Here's the magic. So let's say that I don't have a whole mole of nitrogen, but I only have half a mole of nitrogen. I want to figure out, if I have half a mole of nitrogen, how much ammonia can I make? If I have half a mole of nitrogen, how much ammonia can I make? Well, I have a ratio of 1 nitrogen to 2 ammonias. So if I only have half a nitrogen, how much ammonia could I make? What do you think? Any guesses? One to 2 is equal to 0.5 to 1. Exactly. I can make 1 mole of ammonia if I have half a mole of nitrogen gas. Those lovely railroad tracks we've been using to do our conversions, we can use those for this too. I'm going to start with my given. My given is 0.5 moles of nitrogen gas. I want to flip my nitrogen into ammonia. Since I have nitrogen on top, I'm going to put nitrogen on the bottom. I'm looking for ammonia. I'm going to put ammonia on the top. If I go back a screen, I'm looking for my mole ratio with nitrogen on the bottom and ammonia on the top. This one. I know that there are 2 ammonias for every 1 nitrogen, 1 nitrogen. Nitrogen on top and nitrogen on bottom cancels out, just like all the other stuff that we've been canceling out, top and bottom. So then I just have to do some calculations. 0.5 times 2 divided by 1 gives us 1 mole of ammonia, which is exactly what you told me in chat. So far, so good? So far, so good? All right, let's do the next one. So let's say that I've got 7 moles of hydrogen gas, 7 moles of hydrogen gas, and I want to flip that to figure out how many moles of nitrogen I need to react with all that hydrogen. I have hydrogen on the top. Where should I put hydrogen now? On the bottom, yeah? Good. But I want to flip my hydrogen into nitrogen, so where should I put nitrogen on my railroad tracks? On the top, of course. What numbers should I put in my ratio? Well, I've got 1 N2, and I've got 3 H2s. H2 top and bottom cancels out. Multiply across the top, divide along the bottom, and we end up with 7 times 1 divided by 3. So we could say 7/3 of a mole of nitrogen. Or we could convert it to a decimal, 2.3, repeating, moles of nitrogen. So far, so good? So far, so good? All right. All right. Let's do this one. We'll do this first one together, and this next one I'm going to let you do on your own. So, how many moles of oxygen gas are needed to produce 1.4 moles of water? Can I go ahead and start putting together my mole ratios? I can't. Why not? What's wrong with my screen right now? What don't I have yet? I don't have a balanced equation. I have an equation, but it's not balanced. Exactly, my equation's not balanced. So we need to start with that. I have 2 oxygens here, only 1 here. I'm going to put 2 there. So I have 2 oxygens and 2 oxygens. I have now 4 hydrogens. So we need 2 here. So I have 2 hydrogens to 1 oxygen to 2 waters. Now I can actually use my ratios to do some stoichiometry. This is my given. We always start with the given. 1.4 moles of water. I want to flip that water into oxygen. So I'm going to put water on the top or bottom. Should I put water on the top or bottom? Water on the bottom, because I want it to go away. I want to flip my water into oxygen. This is my wanted. So I'm going to put oxygen on the top, oxygen and water. What number should I put in front of oxygen? Careful. What should I put in front of oxygen? 1. What should I put in front of water? 2. Exactly. Perfect. So now water top and bottom cancels out. 1.4 times 1 divided by 2 gives us 0.7 labels that are left, moles of oxygen. Good. All right, do this one on your own. I'm going to put 1.5 minutes on the calculator, timer on the clock, also called my phone. You've got 1.5 minutes to do this one on your own. Get ready, get set, go. All right, so hopefully you put your given at the beginning, 0.3 moles of oxygen gas. We want to flip that into hydrogen gas. I'm going to put O2 on the bottom, put H2 on the top. In front of O2, I'm going to put a 1. In front of H2, I'm going to put a 2. Top and bottom, my oxygen gas cancels out. We're left with moles of hydrogen gas. We do that calculation, 0.3 times 2 divided by 1. We end up with 0.6. Perfect. Good? Not terrible? Makes sense, kind of, sort of? We're stoichiometry rock stars. All right. I'm going to throw in just a little bit of a vocabulary word here that we're going to talk about more next class. But sometimes in these questions, you're going to hear that you have excess something. That just means that you have more than you need. So if I had a question that said 56 grams of nitrogen gas reacts with excess hydrogen, that just means I don't need to worry about running out of hydrogen. This illustration kind of helps with that. If I have 8 cars and each car needs 4 tires, I can put tires on all the cars and still have 16 excess tires. So that just means I can react all that nitrogen and I'm not worried about running out of hydrogen. So let's go ahead and do this problem now that we know we don't have to really worry about excess hydrogen. I have 56 grams of ammonia, 56 grams of nitrogen gas, and I want to make some ammonia. What's our given? Perfect. 56 grams of nitrogen. What's my wanted? The ammonia. Perfect. So we always start our railroad track with the given. 56 grams of nitrogen. So I need to put nitrogen on the bottom and ammonia on the top. And this, my friends, is wrong. Why is this wrong? Why is that wrong? Why can't I do that? Why can't I just multiply 56 by 2? So in this one, our equation actually is balanced already. That's a really good insight. Definitely make sure your equation is balanced. I do have a balanced equation. And these coefficients, they give me what kind of ratios? What ratios did we talk about? We're not worried about hydrogen. We know that we have plenty. What did we call these ratios? I'm going to go back a couple screens. What did I call these ratios? Mole ratios. Let's go forward. What's I got? Yeah, we got to turn our grams into moles. I can't use a mole ratio if I don't have moles. So we're going to back up. We're going to get rid of this for now. It's going to come back in a little bit. But our first step is to use a mole ratio. I have to have moles. So let's convert our grams into moles. How do I get rid of grams? I've got grams on the top. I'm going to put grams on the bottom. Perfect. Turn my grams into moles, put moles on the top. How many grams in 1 mole of N2? Handy on the periodic table, nitrogen is 14.007. So N2 would be what? That times 2, right? 28.014. So calculator, 56 divided by 28.014 gives us 1.999, lots of decimal places. We're going to use, we need to keep 1 2 sig figs. Keep 1 2, that 9 is going to turn that 9 into a 0, which turns the 1 into a 2. So we've got just about 2 moles of nitrogen gas. Now that we have moles, we can use our mole ratios. So 2 moles of ammonia. Oops, oh my gosh, nitrogen. I keep calling it ammonia. It's still nitrogen. 2 moles of nitrogen. I'm going to now go ahead and use my mole ratio. I have nitrogen. I want it to go away. I'm going to put it on the bottom. I want to flip it into ammonia. I'm going to put ammonia on the top. I'm going to use my mole ratios, 1 N2 and 2 NH3s. So now top and bottom, nitrogen and nitrogen cancels out. 2.0 times 2 divided by 1 is going to give us 4 moles of ammonia, which is kind of the answer to my question. But what if I needed that in grams? What am I going to do now? How do I turn my moles into grams? Another chunk of railroad track. I have moles on top. I want to get rid of my moles. I want to put my moles on the bottom. I want to put my moles into grams, put my grams on the top. How many grams in 1 mole of ammonia? So this was nitrogen, because I was talking about nitrogen. Here, now I'm talking about ammonia. So I'm going to have to do 14.007 plus 3 hydrogens, 3 times 1.008. 14.007 plus 3 times 1.008 gives us 17.031, 17.031 grams in 1 mole of ammonia. So now moles and moles cancel out. I have grams of ammonia left. 4.0 times 17.031 gives us 68.124. I'm going to keep 1, 2, sig, figs, 1, 2. That 1 leaves that 8 and 8. Final answer, 68 grams of NH3. Good? Good? Good. All right. So this map is kind of showing us what we just did. So we were given grams. Grams is mass. G for given. We're going to take our given and turn it into moles by dividing by the molar mass. Then I'm going to use my mole ratios, the coefficient of my given, the coefficient of my wanted. I have given here, I'm going to put it on the bottom to make it go away, flip it into my wanted. So now I have moles of the wanted. In the question that we just did, we're looking for mass again. So then I followed this path, multiplied by the mass of the wanted from the periodic table, and voila, final answer. But you could follow this path lots and lots of ways. Just think about what you're given, what you want, and then you can follow all those pieces. If that path makes, if you like that kind of visual diagram. All right, let's do this one. Now we're going to add some volume to our stoichiometry. So my equation is balanced already. That's kind of nice. My given, my wanted. Assuming STP, remember that's standard temperature and pressure. You know that at standard temperature and pressure, there's 22.4 liters in 1 mole of a gas. I want to figure out how many liters of oxygen, there's my wanted, are required to produce 19.8 liters of sulfur trioxide. There's my given. We always start with the given or the wanted. What should I start with? Always start with the given, exactly. So start with that given, 19.8 liters of SO3. Step 1, turn my liters into what? Turn the liters into moles. Yes, we always have to convert to moles first. I have liters on top. I want liters to go away. I'm going to put liters on the bottom. Put moles on the top so that liters cancels out. What do I know about liters and moles? What do I know about liters and moles? Exactly. There are 22.4 liters in 1 mole at STP. So now I've canceled out liters. I have moles. As soon as I have moles, I can use my mole ratios. So you could stop here and do a calculation, or you can take a little bit of a shortcut and just kind of mash everything all together and then do all the calculating at the end. Either way, it's going to get you the right answer. Do the one that makes your brain happy. So the last one, I did piece by piece. Now I'm going to smash it all together. So I've canceled out liters. I have moles of SO3. I want to get rid of moles of SO3. I want to flip my SO3 into oxygen. I want to flip my SO3 into oxygen. So I'm going to put SO3 on the bottom because here it's on the top. SO3 on the top, SO3 on the bottom. Flip my sulfur trioxide into oxygen, put oxygen on the top. When I flip chemicals, I use mole ratios. O2 has a 1. SO3 has a 2. So now what we've canceled out, SO3, top and bottom, gone. What are we left with? moles of oxygen, which is so close to what we're trying to find. I have oxygen, but I want liters, not moles. So I need to tack one more little piece onto railroad tracks. I have moles on top. I want moles to go away. I want to turn my moles into liters. So I'm going to put moles on the bottom. I'm going to put liters on the top. What do I know about moles and liters? There's 22.4 liters in 1 mole. Do I need to memorize that? No, it's on my list of constants and conversions. But I've been doing this long enough, I do have that memorized. 22.4 liters in 1 mole. So now top and bottom, what cancels out? I've got moles on top and moles on bottom cancel out. What unit labels are left? I have canceled out everything except oxygen and liters, which is exactly what I wanted. Liters of oxygen. Liters of oxygen. So now I'm going to multiply by everything on the top, divide by everything on the bottom, multiply by everything on the top, divide by everything on the bottom. Handy dandy calculator. 19.8 times 1 times 1 times 22.4 divided by 22.4 divided by 2 divided by 1. What do we get? Yeah, 9.9 liters of oxygen. Good? Who's like stoichiometry is fun? No? No? Really? I kind of love it. I kind of love the puzzleness of it. All right. There might be some of you who like it. And there's a special for you. Of course. All right. Do we want to do one more together, or are you ready to work on your own? One more together or on our own? What do we think? Chat says, one more together? All right, one more together. So we're gonna always, oh dear, my pen turned off again. There it goes. Always start with our givens and wanteds. So assuming STP, how many liters of SO3 can be produced with 48 grams of oxygen react? Which one is my given? Which one is my given? 48 or I don't know. 48, yep. So when we're given the data, that's our given, which means that the other thing is our wanted. We're given 48 grams of oxygen. We want to figure out how many liters of sulfur trioxide. My equation, happily, is already balanced. So I can go straight to railroad tracks, start with my given. I've got 48 grams of oxygen gas. Step 1, what do I need to do? What do I need to do with my grams of oxygen? Convert it to moles. Exactly. Always go to moles first. I've got grams on top. Oh, I turned the pen off again. I've got grams on top. I want grams to go away, so I'm going to put grams on the bottom. I'm going to turn my grams into moles, put moles on the top. I need to look at my handy dandy periodic table to figure out the mass of oxygen. Oxygen, according to the periodic table, is 15.999, but it's in O2. So I have to do 15.999 times 2, which is 31.998 grams in 1 mole of oxygen gas. So I have canceled out grams on top and grams on bottom. I now have moles of O2. As soon as I have moles, what can I do? What can I do with moles? Not yet. So if I convert moles to liters, I'm going to have liters of oxygen. If I convert moles to liters, I'm going to have liters of oxygen. I don't want liters of oxygen. Yeah, we're going to use our mole ratio to flip what into what? Use my mole ratio to flip, oopsie, oxygen into SO3. Yeah. So we're going to go ahead and flip our chemicals now. As soon as you have moles, you can use the mole ratio to flip your chemicals. I want to get rid of oxygen. I want to turn my oxygen into SO3. So oxygen is a 1. SO3 is a 2. I have now successfully gotten rid of oxygen. Oxygen on top, oxygen on bottom, voila, gone. I now have, check our labels, moles of SO3. SO3 is good. Do I want moles though? Nope. What do we need to turn our moles into now? Now we can turn our moles into liters. So, one more chunk of railroad track. I have moles on top. I want it to go away. I'm going to put moles on the bottom. I want to turn my moles into liters. Put liters on the top. What do we know about moles and liters? Add STP. 22.4 liters in 1 mole. 22.4 liters in 1 mole. What have we canceled out now? Moles on top and moles on bottom. Voila, gone. Last step, let's do some calculating. Multiply everything on the top, divide by everything on the bottom. 48 times 1 times 2 times 22.4 divided by 31.998 divided by 1 divided by 1, and we get 67.204200. Oh my goodness, so many decimals. How many should I keep? How many sig figs are we going to keep? 2, exactly. 1, 2. That 2 is going to turn that 7 into a 7. It's going to stay right there. Final answer, 67. Check our labels. Liters of SO3. Good? 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 Who's still awake? Good. All right. Yes, people in chat, it's hard, but awake. I will take that awake. Together or on our own? One more together or on our own? What do you think? How about a guided on our own? So we'll kind of do halfsies. First step, what should I do? It totally says it in the first bullet point. What should we do first? For sure, balance. Go ahead and do that. Hopefully we got a 1, 2, 1, 1. Good. Now what? Read the question. I need to find what and what. What should I identify in the question? Yeah, wanted and given. So how many grams of tin 2 fluoride? This is what we want to find. Reacting 7.22 times 10 to the 23rd molecules of HF. This is our given. What should I start my railroad tracks with? Always start with the given or the wanted. Start with a given, exactly. 7.22 times 10 to the 23rd molecules of HF. Now I want to turn my given into what? Turn those molecules into moles, exactly. Always go to moles first. We're going to do that by flipping molecules on the bottom into moles on the top. What do I know about molecules and moles? What do we know about molecules and moles? We know 22.4 liters in 1 mole. How many molecules in a mole? How many molecules in a mole? Yes, Avogadro's number, perfect. 6.02 times 10 to the 23rd molecules in a mole. So I'm going to put that on the bottom so that molecules goes away. 6.02 times 10 to the 23rd molecules in 1 mole. So now top and bottom, what have we canceled out? Molecules. I have moles of HF. What should we do next? Yes, exactly. I want to get rid of that HF. I want to flip it into SNF2. So I'm going to put HF on the bottom to make it go away. I'm going to put SNF2 on the top. What numbers should I put in front of those? What goes in front of SNF2? And what goes in front of HF? Good, good. So now we have canceled out. HF gone, top and bottom. I have moles of tin 2 fluoride. Do I want moles of tin 2 fluoride? Caroline, you could, because, if you're not looking at chat, Caroline just asked, could I do this first and this second? You could. Multiplication and division is commutative, which means that it doesn't really matter what order we do it in. I find that sometimes students forget to convert to moles if we use the mole ratio first. So as long as you know that at some point you need to get rid of those molecules, you're golden. It seems like we're most successful if we keep in our heads must convert to moles first. It helps us remember to convert to moles. But you certainly could rearrange. It doesn't matter what order we multiply and divide in, you're going to get the same answer at the end. Good? Does that answer your question? Good. All right. Last step, we need to convert our moles into grams. So I'm going to put moles on top. Oops, I'm not going to put moles on top. I have moles on top, so I need to put it on the bottom to make it go away. I want to turn my moles into grams, put grams on the top. So since I'm talking about tin 2 fluoride, I need the molar mass of tin 2 fluoride here. How many grams in 1 mole of tin 2 fluoride? Tin is 118.711. Fluorine is going to be 2. I've got 2 of them, 18.998. Add those together. 118.711 plus 2 times 18.998 gives us 156.707. So now, moles on top and moles on bottom cancel out. What are we left with? Grams of tin 2 fluoride, which is exactly what our wanted is. So multiply by everything on the top, divide by everything on the bottom, and we get 7.22 times 10 to the 23rd times 1 times 1 times 156.707. divided by 6.02 times 10 to the 23rd, divided by 2, divided by 1, and it looks like we have a grand total of 93.9721 oodles and oodles of decimal places. How many sig figs should we keep? How many sig figs are we going to keep? 3. 1, 2, 3. 1, 2, 3. That 7 is going to turn that 9 into a 0, which is going to turn that 3 into a 4. There's our 1, 2, 3 sig figs. Label grams of tin 2 fluoride. Voila! Who loves stoichiometry now? Hopefully we all do, because practice. And then there's another quiz. I'm still working off old. I put all these together before the great snowstorm of 2021. So we were supposed to do this last week, not this week. So that's actually a Wednesday, not a Thursday. Good? If you have questions, if you are struggling, what are some actions that you can take to help yourself? Do the homework. The homework is really helpful. I promise I'm writing the homework to try to make it the practice that you need. It's not meant to be busy work. If you're doing this and you're like, it's so easy, then don't waste time doing the homework. But if you're sitting here going, I don't know what just happened, friends, do the homework. That practice, I promise, is helpful if you need the practice. So work on the homework. It is on Canvas. Wednesday's class, just like our last couple classes, 1:45 to 2 p.m. will be quiz time. I'll go ahead and release the quiz early if you like to start it a little bit earlier. But I do want to make sure that you have class time to work on it so that it's not homework. Question.